Hi, in today's class, we're going to talk about why electron cannot exist inside the nucleus. And we will explain it in mathematical ways. We will give proper mathematical reason for that, okay? So in order to understand why electron cannot exist inside the nucleus, we need to know the uncertainty principle of Heisenberg. So, Werner Heisenberg proposed his uncertainty principle in 1927, and this principle states that it is fundamentally impossible to measure certain pairs of physical properties such as position and momentum simultaneously with arbitrary precision. So let me clarify what it really means. It means that if you want to calculate, if you want to find out the position and momentum of a particle with absolute certainty, with absolute precision, it is going to be impossible. It's not going to be impossible because of the devices, because of the instrument that you use. It's going to be impossible because of nature, because the natural laws does not allow it. Okay, this is what just Heisenberg uncertainty principle states. So there is this mathematical derivation for that. We're not going to go into this today. So it has the mathematical form del x times del p, where del x is just the uncertainty in position and del p is the uncertainty in momentum, and the product of these two must be equal or greater than h by 4 pi, where h is just a constant and it is called Planck's constant, as you can see. So to be mathematically precise, mathematically sound, you can say this is del x is basically the standard deviation of x, and del p is the standard deviation of p. So if you multiply the standard deviation of x and standard deviation of p together, then this value must be equal to this certain limit h by 4 pi. You cannot get any smaller than h by 4 pi, which is why you cannot be more precise than a certain limit, right? So I hope you now have at least a slight understanding of what as Heisenberg wants to say and his principle. And let's deep dive into the question that we asked before. So why electrons cannot exist inside the nucleus? So we can use the uncertainty principle of Heisenberg to prove mathematically why an electron cannot be confined within the tiny volume of an atomic nucleus. We know that electron stays in an orbit. So let's call that an electron, and let's call this to be an orbit. So electron is just orbiting its nucleus. Let's say it is orbiting like that, and now you want to find out why it cannot exist inside the nucleus, because nucleus has a certain dimension. It is 10 to the power minus 15 meters. So let's see what we have next. First of all, we find out the diameter of a typical nucleus is approximately 10 to the power minus 15 meters to 10 to the power minus 10 to the power minus 14 meters. So you can consider 10 to the power minus 15 or 10 to the power 14. Some consider 10 to the power minus 15 and some people consider 10 to the power minus 14, which doesn't really matter a lot. So let me clarify. If our electron would be inside the nucleus, then its maximum uncertainty in position would be the diameter of that nucleus, because it is inside the nucleus. So it is inside the nucleus, meaning it's inside the diameter, and which is basically 10 to the power minus 14 meters. So let's calculate del p, which is the standard deviation of momentum, from the Heisenberg uncertainty principle. And Heisenberg uncertainty principle is simply del p times del x is greater than or equal to h by 4 pi, and from here del p is greater than or equal to h by 4 pi times del x. I take this del x down here, right? So now that I have all of this, I can just plug in the value. So my H value I have. Okay, so the H is the Planck's constants, which is basically 6.63 times 10 to the power minus 34 joules second, and 4 pi is just simple constant, and del X is 10 to the power minus 14 meters. So 10 to the power minus 14 meters. I took all of these units in SI unit, right? So if I calculate this guy with a calculator, I get this value, which is 5.27 times 10 to the power minus 21. So my del P is greater than or equal to 5.27 times 10 to the power minus 21 kg meter per second, right? So what does that suggest? So it says is that we can calculate the kinetic energy from del P. So how precise I can be, or how sure I can be about del P? That is 5.27 into 10 to the power minus 21. That's how precise I can be, because it's the smallest value I can get from the Heisenberg uncertainty principle. I can't get any smaller than that, right? So I can find out the kinetic energy from that, and we know that kinetic energy and let's say kinetic energy and momentum is related by this equation, E is equal to P into C, because it's a relativistic energy formula, and it's safe to use this, right? So where did I find this formula from? I have E square equal to P square C to the power C square plus M naught square C to the power 4. So for an electron, the mass is so tiny, its rest mass is so tiny, so I can basically neglect this part, and I can say that my E square is equal to P square C square, and from there I can say that E is equal to P times C. So if that's the case, I can plug in the value of P here, and my C value is 3 times 10 to the power 8 meter per second. And if I calculate that, and I did calculate that, and I found out that my energy is 1.58 times 10 to the power minus 12 joules, which is basically 10 mega electrovolt. It is if converted into mega electrovolts. You can always, I think you can do that of your own. That calculating from joule to mega electrovolt is no brainer, right? So then you can see here that the kinetic energy is 10 mega electrovolt, which is interesting because of the experiment results that we have so far. So experiments that show that electrons emitted during beta decay, you know why is so experiments show that electrons emitted during beta decay have energies around 2 to 3 mega electrovolt. If an electron were trapped inside the nucleus, it would be at least 10 mega electrovolts, as you can see from the calculation. So to stay there, furthermore, the attractive potential of the nucleus is not strong enough to hold an electron with such a high energy. So let me make it clear to you that from the calculation we saw that the energy must be 10 mega electrovolt at least to stay inside the nucleus. So for an electron to stay inside the nucleus, it must have 10 mega electrovolt energy, which speaking of which, our nucleus is not even capable of holding an electron with such an high energy. That's the one logic. And the second one is that, which is the most powerful one, is that in the case of beta decay, you see electrons or beta particles are only 2 to 3 mega electrovolt, which are emitted from the nucleus, right? Because beta particle emits from the nucleus. Beta particles are basically like electrons. They are electrons, but they come from the nucleus. And if electrons really could stay inside the nucleus, then in the process of beta decay we could have seen energies from this beta particle to be at least greater than or at least equal to 10 mega electrovolt, which we don't see. We only see 2 to 3 mega electrovolts electrons. So which suggests, so we have two kind of logic. First one is this and the second one is this. So for these two reasons, you can finally conclude that this is the reason electron cannot stay inside the nucleus. This is one of the most asked questions. It's one of the most asked questions in physics exams. Hopefully now you can answer that. Subscribe to my channel for more videos like that. See you.